Hello everyone, welcome to this lecture on permutations and combination. Just to quickly recap, in the last lecture we started our discussion on combinatorics and we discussed the basic counting rules like the sum rule and the product rule. So in this lecture we will recall your concepts related to your permutation and combination that you might have studied during your high school, and we will also discuss about combinatorial proofs. So to begin with, what is a permutation of a set of objects? So as the name suggests, it's an ordered arrangement of objects. And when I say the ordered arrangement of the object, that means the ordering of the objects matter here. So for instance, if I consider two objects, say object person number, if I consider two persons, sorry, person number one and person two, then uh, these two orders are different. If I consider person number one followed by person number two, then this order is different than the ordering where person number two is appearing before person number one, right? So we define what we call as R permutation, and R permutation is nothing but an ordered selection of R elements from a set, right? So you are given a set which has certain number of elements. Of course, it should have R or more number of elements, and the number of ordered selections of R elements from such a set. Okay, so if you select R elements in an ordered fashion, then that's called an R permutation, and the number of such R permutations from a set consisting of n distinct elements is denoted by this quantity or this permutation function p of n comma r, right? So you are given a set with n distinct objects, and we want to find out how many R permutations I can have from this set. Okay, so for instance, if I consider n equal to 3 and r is equal to 2, then the output of the function p of n comma 2 will be 6. Why? Say you have three persons, person 1, person 2 and person 3, right? So you have a set of three objects or three persons here, and I want to find out how many two permutations I can have, how many ordered selection of two elements I can have from this collection. So pictorially, these are the six possible ordering, right? I can choose person number one followed by person number two. That's one ordering. I can choose person number one followed by person number three. That's another ordering. I can choose person number two followed by person number one as one of the orderings. I can have person number two followed by person number two as another ordering. In the same way, I can have person number three followed by person number 2 as one of the orderings, and I can have person number 3 followed by person number 1 as another ordering, right? So these are the different possible two permutations that you can have from this collection of three people. So now it's easy to see that if I apply the product rule, then I can derive a formula for the function p of n comma r. And the output of the function p of n comma r is nothing but the product of n minus 1, n minus 2 up to n minus r plus 1. Of course, for this formula to make sense, you require your r to be in the range 1 to n. Otherwise, you get into the issues of negative quantities and so on. So how exactly we get from product rule the output of p of n r function to be this? So you can imagine that I have r slots to be occupied. Okay, and I have n objects to choose from. I have object number x1 to xn. Now, when it comes to the first slot, here I can put either object number x1 or object number x2 or object number xn. So that's why I have n choice for the first object or first slot here. Now, once I have decided which of the n objects to put in the first slot, corresponding to that, I have now n minus 1 options or n minus 1 objects to choose from to put in the second slot, and so on. By the way, here repetitions are not allowed because right now I am considering the case of selecting or forming R permutations, where in the permutations repetitions are not allowed. So that's why when I am considering the second slot here, right, I can't consider the object which I have been already assigned to the first slot. So that's why I have only n minus 1 options instead of n options to choose from when it comes to the second slot. Okay, the formula becomes different if in the permutation that I am forming, the repetitions are allowed. Right. So now it's easy to see that by applying the product rule, I get the output of this p of n r function to be this value. Right. Now we can define p of n comma 0 to be 1, namely no way of permuting zero objects. So if you are given n objects and you don't want to select any objects or you don't want to permute any object, then that can be considered as one way of doing that, right? Because there is no way. So no way is considered as the only way of permuting zero objects. So that's why we define p of n comma 0 to be 1, right? That's defined, right? It's not coming from the product rule. That is coming as part of our definition. So now we have the value of p of n comma r, where r is non-zero and in the range 1 to n, and we have the value of p of n comma r when r is 0. So if I unify these two if I unify these two values, uh, then sorry for this. If I unify these two values, I get that p of n comma r turns out to be factorial n over n minus r factorial. Okay, you can easily verify that. Okay, now we consider the case when we are selecting objects, but while selecting the objects, the order does not matter. That means we are now interested in unordered selection of our elements from a set, and each such unordered selection is called as an R combination. Okay, so that means if I am now selecting two objects out of three objects, then it doesn't matter whether I pick x1 before x2 or whether I pick x2 before x1. Both this, so the arrangement x2 comma x1 will be considered the same irrespective of whether x1 comes before x2 or whether x2 comes before x1. Okay. So we use this notation C function or the combinatorial. This is often treated as choosing uh, R objects from a set of indistinct objects, right? And this function basically denotes the number of R combinations that we can have for a set which has n distinct elements. Okay. So again, you must have studied it during your high school that the output of this function or the value of this function is nothing but n factorial over r factorial times n minus r factorial. So there are several ways of deriving that. The simplest way could be to find out a relationship between the permutation function and the combination function. So my claim is that the output of the permutation function, namely p of n comma r, is nothing but the product of the C function, namely C of n comma r multiplied with P of r comma r. Why so? Because if you see the left hand side, it is nothing but the number of ordered selection of R elements. So you are given a set with n objects and you are interested to find out how many ordered R permutations you can have over a set consisting of n elements. That's nothing but your function P of n comma r. My claim is the number of ordered selection of R elements is nothing but the following. You first find out the number of unordered selection of R objects, or equivalently find out how many ways you can first select those R elements which you want to order in your permutation. And that you can do in C of n comma R ways. Now once you have decided which R elements you are going to put in your permutation, right? Right now, you are considering the unordered selection of those R elements. If you if you have decided the R objects, then the number of ordered arrangements of those selected R elements, if you multiply that with the number of unordered selection of R elements, that will give you the total number of ordered selection of R elements, right? So it's like saying the following: the, you have a set x1 to xn. You first decide the R objects for permutation, right? Where the order does not matter as of now. This can be done in C of m comma r ways. Now, once you have decided that I have selected object number xi1, xi2, and say up to xir, you have selected these R objects. Every arrangement, every possible ordered arrangement of these R elements will give you one possible permutation. And how many ordered arrangement of this R objects you can have? You can have P of R comma R such ordered arrangements, right? So that will give you the total number of R permutations that you can form from this subset of R elements xi1, xi2, xir. So that's the relationship between the P function and the C function. So now your goal is to find out the find out the value of this C of n comma r function. So you just take this P of r comma r in the denominator, and P of r comma r is nothing but r factorial. That's how we get the value of the C function, right? Fine. So till now we considered the case of permutations and combinations where repetitions were not allowed. Now we will consider the case where even in the ordering, in the selection, the repetitions are allowed as well, right? So we are now interested to first find out the number of R permutations of a set of objects where I am allowed to have repetitions. So for instance, if I consider a set with three persons, right? Say person 1, person 2, and person 3. Now if I ask you how many two permutations I can have over this set where I can repeat the person when I'm forming the permutation. It now turns out that instead of six possible permutations, I will now have nine possible permutations. The six possible permutations which we had earlier where repetitions were not allowed, they will be still present, right? So those permutations are still present here. Right? So these were the six permutations which were there earlier when the repetitions were not allowed. But now, since I am allowing you repetition, I can have a permutation where I have person 1 followed by person 1. Similarly, I can have, okay, so sorry for this. This was not there earlier. This permutation was there earlier. I can have a permutation where I have P2 followed by P2, and I can now have a new permutation where I have P3 followed by P3. These are all allowed now because repetitions are allowed in this case. So now again, if I want to find out the number of R permutations of a set of n distinct elements where repetitions are allowed, then it turns out to be the product of n R number of times because I have to fill R slots, and the first slot can be occupied in n ways. And for each of those n ways in which I can occupy the first slot, I can fill the second slot also in n ways because repetitions are allowed. And now, corresponding to each of the ways in which I would have filled the first two slots, I have n ways to fill the third slot and so on. So that's why the total number of R permutations of n distinct elements that I can form is n power R. Now let's try to find out the number of R combinations where repetitions are allowed. And this is slightly tricky. Okay. So before going into the derivation of this formula, let me give you a motivating example, and then we will try to relate this example with the problem of coming up with a number of R combinations where repetitions are allowed. So consider the following. You must have seen cash box when you go to supermarket and do the billing. So in cash box, you have various slots available. Each slot is occupied with a currency of some specific denomination. So imagine you have a cash box which has four slots. The first slot has bills of $1, right? Many bills of $1. The second slot has many bills of $2. The third slot is for $5 bills, and the fourth slot is for $10 bills. And of course, okay, so by the way, in this problem, when we are finding the number of R combinations with repetition, right? So I consider that the objects in the set from which you want to find out the R combinations, each object has many copies available, okay, and each of those copies are uh, indistinguishable. So, for instance, in this example, I am assuming that in the $1 bill slot, you might have several $1 bills, and all those $1 bills are indistinguishable. That means you can't say that, okay, if I choose the $1 bill which is on the topmost position, then that will be considered different from the $1 bill which is present at the bottom, right? So I won't consider those things here because I will be assuming, I will be making the assumption here that the bills of each denomination are indistinguishable. That's important while deriving the formula. Now suppose my problem is the following. I want to select total three bills from the bills which are available in the cash box, and here order does not matter because I am interested to find out a number of R combinations. Yeah, R is equal to 3 here, okay, and N is equal to 4 here, okay. You have four types of objects, namely object of type $1 bill, object of bills of type $2, bills of type $5, and bills of type $10, and you have many copies of them, okay. At least three copies of bills of each denomination is available. And your goal is to find out how many ways you can pick three bills in total where the order does not matter. So, for instance, one way of picking three bills is you pick all $1 bill. That means you pick three $1 bills, or you may decide to pick one bill of $1 and one bill of $2, or you may decide these are the, or you may decide to pick a one $5 bill, one $2 bill, one $1 bill, or you may decide to pick all the three bills of $10 type and so on. So these are the various ways. Okay, our goal is to find out how many such selections are possible. So for finding that, consider the following mapping. Okay, so what I do is I think in my mind that in your cash box, the bills of various denominations are separated by a boundary, right? So you can imagine that that boundary is nothing but a vertical line. So you have a vertical line or a boundary between the $1 bills and the $2 bills in the cash box. Similarly, you have a boundary here, you have a boundary here. Okay. Now suppose I pick bills of $1 in three numbers, right? So remember, my goal is to pick three bills in total. So one way of doing that is I pick three $1 bills. So I represent this selection by saying that I have picked three $1 bills. So I put three cross under the heading one, and I don't put any cross under $2 denomination, $5 denomination, and $10 denomination, right? So I can say that there is a mapping here between a possible way of selecting three bills. So here is a way of selecting three bills where I have picked three $1 bills, and corresponding to that, I am giving you a string consisting of three crosses or three cross and three vertical lines. Now consider this way of selecting three bills. I pick two $1 bills and I pick one $2 bill. So my claim is corresponding to that I can associate this string where I put two cross under $1 because I have chosen two bills of type $1, and I put one cross under the $2 denomination because I have chosen one bill of $2. Under $5 and $10 I do not put any cross. So I can say that corresponding to this way of selecting three bills, I can associate this string of three cross and three vertical lines. In the same way, if my way of picking three bills is the following, namely picking one $1 bill, one $2 bill, and one $10 bill, then the corresponding string will be to put one cross under $1, one cross under $2, and one cross under $10. And now I can say that I have a bijective mapping, okay, namely one-to-one onto mapping. I can associate, so whatever mapping I have discussed till now, my claim is that that is a bijective mapping, namely a one-to-one onto mapping between the set of all possible ways of selecting three bills out of bills of four denominations in an unordered fashion, and a set of all strings of length 6 where there are three crosses and three vertical lines. My claim is that the mapping that I have discussed is a bijection. Of course, it is an injective mapping, right? From this direction to this direction. Why so? Because you take two different ways of selecting three bills. The corresponding string of three cross and three vertical lines will be different. And my claim is that this mapping is surjective as well. You give me any string of three cross and three vertical lines, I can tell you a corresponding way of picking three bits. So for instance, if you give me a string like say, okay, then what is the corresponding way of picking three bills here? So here no bill of type $1 will be picked, and all the three bills of $2 type will be picked, and no bill of $5 will be picked, and no bill for $10 will be picked. So this mapping is subjective as well. So since I have two sets here and I have defined a mapping which is one to one, namely injective and subjective as well, this mapping is a bijective function, and that means the total number of ways of selecting three bills is equivalent to finding the total number of strings of length 6, which has three cross and three vertical lines. And it's easy to see that the number of such strings is this. Why? Because your string is of length 6 and you have to choose three positions where the cross has to appear. Because once you decide the three positions where the cross is going to appear, automatically at the remaining three positions on the problem definition, the vertical line will be present. So you don't have to worry about the remaining, you don't have to worry about the positions or the three positions where the vertical lines are going to appear. Because once you have chosen the three positions where cross are going to appear, the remaining things are automatically frozen for vertical line to appear. And why I am writing it in this form, 4 minus 1 plus 3, because in general, the general formula for the general line NR will be C of n minus 1 plus R cross R. Because how many vertical lines will be there if the number of objects of various types is n? So you will have you will have n slots because you have objects of n type, right? So you will have object of type 1, and then there will be a vertical line, and then you will have object of type 2, you will have one vertical line, and like that you have an object of type n. So how many vertical lines will be there? N minus 1. And how many cross positions you have to fill? You have to fill r cross position. You have to fill r number of cross positions. So that's why the length of the string will be n minus 1 plus r, because it will have n minus 1 number of vertical lines and r number of cross symbols. So that's why the general formula for R combinations where repetitions are allowed is C of n minus 1 plus r comma r. Okay. So now let's see some examples of combinations with repetitions. This is a very interesting formula which is used in lots of counting problems. So suppose I want to find out the number of integer solutions for the equation x1 plus x2 plus x3 equal to 11, where x1, x2, x3 can be are allowed to be greater than equal to 0. So my claim is that the number of solutions is nothing but the number of all strings of 11 crosses and two vertical lines. This is because you can interpret this formula, you can interpret this problem as the following. You have bills of type x1, bills of type x2, and bills of type x3. Your goal is to pick total 11 number of bills. You can pick all the 11 bills of type x1. That's one possible solution, which corresponds to x1 being 12, x1 being 11, and x2 being 0, and x3 being 0. Or you can pick 10 bills of type x1 and one bill of type x2, which corresponds to x1 being 10 and x2 being 1. Or you could have x1 equal to say 6, x2 equal to 4, and x3 being 1, which corresponds to picking 6 bills of type x1, 4 bills of type x2, and 1 bill of type x3. And here order does not matter. So that's why your problem now reduces to picking total 11 number of bills from bills of 3 possible denominations where order does not matter and where repetitions are allowed. And we have derived just now that the formula for that is nothing but this quantity, right? Now suppose I change the problem slightly. I am now interested to find out the number of solutions where x1 is greater than equal to 1, x2 is greater than equal to 2, and x3 is greater than equal to 3. Earlier, it was allowed that x1 could be 0, but now x1 is not allowed to be 0. x1 has to be at least 1, x2 has to be at least 2, x3 has to be at least 3. So my claim is that this is equivalent to finding the number of solutions for this new equation where there is no restriction on x1, x2, x3. That means any of them can be 0. Why so? Because again, if I consider the bill analogy, you have bills of denomination x1, x1 type bills, right? You have x2 type bills, and you have x3 type bills. Okay. Now, x1 greater than equal to 1 means definitely I have to choose one bill of type x1. My goal is to pick 11 bills, right? Out of those 11 bills, one bill has to be of type x1. Two bills have to be of type x2, and three bills have to be of type x3. That means the problem already states that I have already chosen 6 bills. Definitely I have chosen one bill of type x1 and two bills of type x2. So total 3 bills I have already chosen, and 3 bills of type x3. That means 3 more bills are already chosen. So 3 plus 3 is 6. So 6 bills are already chosen. My goal was to pick 11 bills. So now I am left with the problem of choosing 5 bills. And now for choosing these 5 remaining bills, I have no restriction. I can pick all of them of type x1 or all of them of type x2 and all of them of type x3, or one bill of type x1 and 4 bills of type x2, or one bill of type x1, 2 bills of type x2, and 2 bills of type x3, and so on. So the number of, and now we know how many ways I can satisfy this equation where there are no restriction on x1, x2, x3. That will be nothing but C of, I have 3 bills, so 3 minus 1 plus R is 5 now, comma. Okay, right. Now let's go to the last topic for today's lecture, namely combinatorial proofs. And again, I'm sure that you have studied it during your high school. So What exactly are combinatorial proofs? These are some common proof strategy which we often use in combinatorics. Namely, it's a counting argument to prove identities where you have something on the left hand side and your right and something on your right hand side, and you want to prove mathematically that your expression in the left hand side and the right hand side are same. But to do that, we use the counting argument, and we prove that the expression in the left hand side and the expression on the right hand side count the same number of objects, but in different ways. But nowhere in the proof we actually expand our expressions on the left hand side or right hand side and show by simplification that left hand side is same as right hand side. We do not do that. That's not the goal of a combinatorial proof. So let's see a very simple combinatorial proof which you must have definitely studied. We will want to prove that the value of C of n comma r is same as the value of C of n comma n minus r. Of course, one way of doing that is I expand C of n comma r and rewrite it as factorial n over factorial r over n minus r factorial. And I expand my right hand side. Okay. And in this case, actually, both the expressions are same. So I could have simply said that they are same. But that's not the goal of a combinatorial proof. In general, when we are giving a combinatorial proof for proving LHS and RHS are same, we do not expand or simplify the expressions in the left-hand side and right-hand side. If you do that, that's not a combinatorial proof. You will get 0 marks if you are asked to prove something by combinatorial proof and you end up simplifying expressions. The way we are going to prove this equation, this equality using combinatorial proof is the following. Suppose you are given n objects, then your left hand side is nothing but the number of ways in which you can pick r objects out of those n objects, right? That's the interpretation of C of n comma r function, right? Now it turns out if for each of the ways in which you can select r objects, there is a way of excluding n minus r objects, right? So I can reinterpret my problem and say that instead of worrying about how many ways I can pick r objects out of n objects, I instead count the number of ways I will decide or the number of ways I will choose the n minus r objects which I want to leave. Because once I decide that these are the n minus r objects which I am going to leave, that automatically gives me the r objects which I will be taking or considering, right? So that's why it's easy to see that the LHS expression and RHS expression are same. And we are counting two different things here. The left-hand side thing are basically, the left-hand side expression basically counts the number of ways you would have selected the objects, whereas the right-hand side expression counts the number of ways in which you would have left objects. Okay, and there is a mapping. Whatever you left, corresponding to that, you are left with objects which you are picking. Now let's prove an interesting combinatorial identity using combinatorial proof. This is often called as Pascal's identity. So to prove this, consider a collection of n plus 1 objects, right? So I am calling those n plus 1 objects as say x1 to x of n plus 1. They are distinct. Now, what is my left-hand side expression? That denotes the total number of k combinations I can have out of those n plus 1 objects, right? I have to pick k objects. I can do that in C of n plus 1 comma k ways. That's the left-hand side. Now I have to show that the same thing can be counted by adding these two quantities that are there on the right-hand side. How do I do that? So my claim is that the different k combinations that I can have out of x1 to x of n plus 1 can be divided into two groups. That will take care of the addition that we have on your right hand side expression. I have to somehow show that the total number of different k combinations that I can have can be divided into two categories, two disjoint categories to be more specific. And those two disjoint categories are the following. You consider all k combinations that you can form from x1 to out of those n plus 1 objects where a specific object is always present. say the object x1 is always present. And the number of such k combinations is nothing but C of n comma k minus 1. Because if the object x1 is always going to be included in the k objects which you are finally choosing, then you have to worry about how many ways you can pick the remaining k minus 1 objects from x1 out of x1 to xn, right? So you had x1 to sorry, you had x1 to x of n plus 1, sorry. So you are always going to choose x1. That's the category we are right now considering. So now you are left with n objects, namely x2 to x of n plus 1, and you have to choose k minus 1 objects out of this remaining n objects, which you can do in these many ways. In each such k combination, you include the object x1 that will give you category 1 of k combinations. Whereas category 2 k combinations are the one where the object x1 is never included. And it's easy to see that the number of different k combinations of this category is C of n comma k. Because if you are not going to include x1, right, then your problem is still to choose k objects, and now you are left with only n objects to choose for those k objects, right? You can choose your k objects only from the collection x2 to x of n plus 1. So you are left only with n possibilities, and the number of k combinations that you can now have in the second category is this. And now, if I focus on the total or the different k combinations that I can have out of this x1 to x of n plus 1, I can have either a k combination of category 1 or a k combination of category 2. Namely, in the k combination, either x1 is there or x1 is not there. I can't have any third possible category. And these two categories are disjoint. There is no k combination where x1 is present as well as x1 is absent. So if I sum the total number of k combinations that I have in category 1 and the number of k combinations that I have in category 2, that will give me the total number of k combinations that I can have for a set consisting of n plus 1 objects. And that's precisely your right hand side. And this is a combinatorial proof because now I have not expanded my left hand side expression. I have not expanded my right hand side expression and simplified them, right? I am just giving a counting argument and proving that LHS and RHS are counting the same things. So that brings me to the end of today's lecture. These are the references used for today's lecture. Just to summarize, in this lecture, we introduced permutations, combinations. We saw the formula for permutations and combinations, both with repetition and without repetition. And we also discussed about combinatorial proofs.